Ladies and gentlemen, this is the lecture for today, which is April 14th. And apparently my internet service is all out. And it has nothing to do with my house. It has to do with the basic neighborhood area. So I'm going to go ahead and record Section 8.6 for you. And so in Section 8.6, we begin with the exponential function. When we look at exponential functions, we want to pay attention where we look at f of x is equal to some base raised to the x power. So this exponential function is noted because the exponent itself is the x. Now, typically in these types of equations, you will notice that some characteristics that stick out are that the graph will always have the point 0, 1, and that is noted because if x is 0, well, anything to the 0 power is 1. Secondly, if we have the base value being a number greater than 1, the graph will rise. Obviously, when we read the graph, remember it's always left to right. Third point, if by chance the b value is a fraction, then we say that the graph falls left to right. So in other words, on this graph will rise this way. On this graph, the graph will tend to have this behavior. All right, and still goes through 0, 1. Fourth characteristic of this is that the x-axis is the horizontal asymptote. And the fifth item to remember here is the domain. So the domain of this type of function is always from negative infinity to positive infinity. The range, mind you, of a traditional function is from 0 to positive infinity, regardless of the behavior. And so the other concept they kind of update you on here relative to this information is natural base e, to remind you that it is in your calculator and that that base itself can also mimic the behavior of this type of function. So if I have f of x is equal to e to the x, it too will exhibit the 0, 1 crossover, and it will also rise in this manner. Remember, e is equal to 2.71828, and that is a repeating value. Aside from this, they also relate you back to remembering the formula of compound interest. So the compound interest formula and so in this case, we have where the future value is equal to the present value times 1 plus r divided by n. Remember, that's a rate over the compounding period, and that is raised to the compounding period times t, and t is time in years. After all of that mix of information, they also remind you of the continuous or continuously compounding Is the internet still down? Okay. The continuous compound interest formula And that is the one that I always jokingly refer to as PERT, where P times natural base E, and that is raised to the rate times time. Remember, the rate is always in decimal form and time is always in years. In example 1, given those two examples, in example 1, they tell you that the p-value, the amount invested, is $1,000. They gave you also that the rate is 0.02 or 0.02. They also tell you that n is compounded quarterly, so n is 4. And what else do they tell you? Time, t, the investment is set for 10 years. And so we basically would apply this to the formula, and they want to know how much money we would have given those parameters. So the principal amount times 1 plus 0.02 divided by 4, and all of this raised to the 4 times 10, which yields us 1,000 times the 0.05, and that is raised to the 40th. Remember that order of operations dictates you do this first and then multiply times 1,000. We're giving us our final answer of $1,220.79, which is how much we would have at the end of 10 years. All right, so that's example 1. Example 2. In example 2, we're applying PERT. So they're telling us that the p-value is, in this case, $5,000, which is being invested. It is continuously compounded at a rate, so you have an interest rate, which is 2.5%. Remember that is really 0.025. Remember, you move the decimal 1 2 places to the left. All right, and so 0.025. They also tell us in this case that time is equal to 4 years, and that is stated in the question. And so if we apply the PERT, this would be A is equal to the 5,000 times E, and this is raised to the 0.025, and that times 4. And we end up in this case with the A value, the future value, equal to $5,525.85. All right, be careful with the order of operations. That's how much you would have at the end of 4 years. Now, exponential growth functions. There is a formula, and so exponential growth, and we would need to focus in this case where A of t is equal to A sub 0, which is the initial amount, times E, natural base E, and that is raised to the k, where if k is greater than 0, it's growth. If it's less than 0, it's decay, times t. Keep that in mind. Then they throw you, after giving you this formula in the middle of the chapter, they begin with logarithmic functions. So let's talk about logarithmic functions. And in this case, we're talking about functions with the word log base b of some value is equal to, I don't know, let's call it n. All right, and so we also refer to this, for example, if I say to you log of base 2 of 8 is equal to 3, the reason for that is because 2 to the third power is equal to 8. All right, and so I just want you to see the association between exponential form and logarithmic form. Okay, So in example 3 in your textbook, they actually go back to the PERT formula, where A is equal to PERT, P times natural base E raised to the R times T. And so they start with the question, suppose that a certain amount P is invested at an annual rate. So they do give us the rate, which in decimal form is 0.015. It is compounded continuously, which is what tells you, remember this is example 3 in your book, and they want to know how long it will take to double. So what time will it take? What time t is the question, will it take to double? So when you see this question, before you start panicking because it seems like they didn't give you enough, remember that if P is the initial amount and I want it to double, then I want 2P. So we still have the P value times E raised to the 0.015, and we're looking for T. We don't know T. What's going to happen here is twofold. First of all, you're going to divide by P, and immediately that's just going to leave us with 2 is equal to E raised to the 0.015 T. Okay, remember that these basically just cancel. So this is when it doubles. You're going to use this process. Because we don't have the same basis now on either side of the equation, we're going to take the natural log on either side of the equation. And now we're going to solve. Now we have natural log 2 is equal to the natural log. Remember, these two cancel each other out. What you really have is natural log of 2 is equal to 0.015 to the t, or times t. So we're going to divide by 0.015 on both sides of this equation. This is going to cancel this value, and therefore t is equal to natural log of 2 divided by 0.015, and throw it into the calculator. You should get 46.21. That's example 3. Okay, example 4. This chapter is very choppy, if you've noticed. I'm just going through what they're giving me here. In example 4, we're going into the same thing where we're modeling this. This question has to do with modeling population growth. So what we have here is the question. According to data from the United Nations, Department of Economics and Social Affairs, Population Division, the world population forecast from 2020 to 2050 is projected given the model where f of x is equal to 2049.73 e raised to the 0.007506x. So they give that to you. They say here in part A what would be the population in 2030. And so understand that this is showing the population model from 2020 to 2050. So that's the date range that they're giving us here. Since they're asking us for 2030, we would say f of 2030 is equal to the 2049.73 e to the 0.007506 And we're looking for x to be 2030 in this case. So when we do the math, and again, this is straight up calculator use, we would find that f of 2030 using a calculator is going to be equal to approximately 8,494,000.
Very cool. Very good.
And I'm sorry, 8,494,000,000, and we're going to leave it at that. Now, in part B, they reverse the script on you. In part B, they tell you, based on the model, in what year will the population reach? Okay, so will the population reach? We're still working on trying to get the internet on the background, so hang tight. Will the population reach 9 billion? All right, and so in this case, what you want to go is backwards. So we would begin by saying then, since we know that this is 9 times 10 to the 9th, and we know that this is equal to 2049.73 e raised to that 0.007506, and then x is what we're actually looking for here. In this case, because this is how they're wording it, the first step we're going to take is we're going to divide by the 2049.73 on both sides, which cancels out all of this, leaving us this value, all of this, equal to all of this. Now remember, we're going to divide by e on both sides, right? Because that's the next step. So if I divide by e, then this becomes the natural log of 9 times 10 to the 9th divided by 2049.73. So that would be the natural log of all of that. And this e is what becomes natural log. This is going to cancel out the e, leaving me this equal to 0.007506 times x. So obviously to solve for x, I would divide by 0.007506 divide by 0.007506 on both sides, canceling all of this out, leaving me x equal to that. I would then find that x is equal to 2038. Now, granted, I worked this out for you in front of you. What I would ask you to do is try this on your calculator, because I think it would help you. All right. The last example I'm covering here, example 5, no luck yet, which is carbon dating, carbon-14 dating. And so in this case, they tell you a formula. They start you with carbon-14 is a radioactive form of carbon that is found in all living plants and animals. It says after a plant or animal dies, the radiocarbon disintegrates. Scientists determine the age of the remains by comparing the amount of carbon-14 present with the amount found in living plants and animals. The amount of carbon-14 present after x years is modeled by the exponential function where we have f of x is equal to a sub 0 times e raised to the negative 0.0001216x, where a sub 0 is the initial amount. They want to know what is the half-life in part A. So notice the steps. what is the half-life of carbon 14? I'm just going to put C14. So that's the first question they give you. And so the solution here would be 1/2 of A sub 0 is equal to the initial amount, A sub 0, E to the negative 0.00012116 x. And so obviously you notice that the A sub 0's, the initial amounts, are going to cancel. Given that information, you now have 1/2 is equal to E raised to the negative 0.00012116x. Because we don't have the same basis, we're going to take the natural log on both sides. And if you remember what I stated about natural log and E, they are going to cancel each other out. So you are now left with natural log of 1/2 equal to negative 0.00012116x. The last step you would take here to solve for x, obviously, is to divide by negative 0.0001216 on both sides. When this happens, all of this will cancel, leaving you x equal to your answer, where x is equal to 5,700. All right, so that's carbon dating. So basically we're working on using our information here to solve for this question. That's the last example I'm covering that I think that you will need. That's basically all of the examples in section 8.6. So section 8.6 has been recorded for you to use.